Good morning, everyone. Welcome to the fourth lecture in the Systems Dynamics course. Before we start, as usual, a few announcements. Now, on Monday, I went to the dentist, and I still suffer. So, actually, I cannot open my mouth so much. That's as much as I can open it. So, if at some point you don't understand what I'm talking about, just stop me and say something. That's one thing. Second thing, I would like to remind the presenting groups from last week to upload their student solutions. At least I didn't see them yesterday, I think in the evening. Is there anybody from these groups who presented last Tuesday? Have you uploaded your solutions? Because, there may also be a problem with the Moodle system, because I may have set up the wrong things. So I want to know if you have problems uploading it or you just didn't bother. But I hope you will upload it by the end of this week. Another administrative thing, this is the fourth lecture. So after the fourth lecture, we'll have an online test. I already talked about these online tests. The online test will probably be prepared tomorrow, and you will have maybe from 4 to 6 hours to complete it, which is plenty of time anyway. In addition to that, there will be more about the online test. I will send an email around. In addition to that, there would be an online survey, which is the other quality control that we do in this course, where you kind of evaluate me. And it will also probably become available tomorrow or maybe on Saturday, I don't know. And then you'll have 1 week to complete this online survey. It's going to be a mixture of multiple choice questions and kind of a manual text input where you can write comments and stuff like that. And then we all discuss. So, of course, it's anonymous. Even to me, it will be anonymous. This is the point. But then we'll all discuss the aggregate results. And I'll show you what the majority thinks. All right. Are there any questions? Yeah. The online test, you will have, let's say, 4 to 6 hours after you start it, but the whole online test would be available for maybe a week. So you will have 1 week to start it. But then once you start it, you have, 4 to 6 hours. If you don't think, if you try to find everything on the slides, it would take you maybe about 30 minutes, I think. About 30 minutes, 20, 30 minutes. But, the point of these online tests is not to make it possible to fail them, unless, of course, you don't want to do them, which is, there is nothing we can do about it. The point of the online test is to simply make you go through the slides. And just by going through the slides and find information, you automatically remember something. All right. Are there any questions regarding the previous lectures or self-studies? Because today we kind of start a new topic. You can ask questions later, and also you can ask any questions during the self-studies regarding the lectures. So let me start. Today I'm going to be using a fancy presenter because those of you who have seen the slides, you saw that there are diagrams and kind of drawings that I simply need to navigate through. And if I use this laser pointer, you can see, but the people watching the recording cannot see. So this kind of makes it very difficult for people to follow these lectures only with the podcasts. So with this thing, I can do a lot of fancy things. For example, I can do like a spotlight thing, right? So for example, this is lecture 4. I can, I can zoom in. This is the professor. Yeah. And this is the email that you should send all your questions to. So yeah, lots of cool things. It kind of makes it difficult to navigate because when I move it, the cursor moves. But anyway, these are petty concerns. All right, let's start. Again, as I will do in every lecture until the end, and as you should expect from me in every lecture until the end, a summary of what we've done so far. We've looked at mostly finding solutions to problems that we already discussed, their nature. These are complex problems, non-trivial problems, multiple criteria problems, and we looked at ways to analyze the situation, to analyze the problem and find solutions for it, and then select what we hope to be the better solution, finally implement it. We looked at the problem-solving cycle as a framework for coming up with solution approaches and selecting solution approaches. We started with project management last lecture. Today we're going to finish project management. It's mostly about implementing solutions. We looked at how projects can be scheduled from time perspective, so the critical path method. Today we're going to be talking about some deficiencies of the critical path method and how we can address them. Hopefully you know the critical path method is the thing which determines your project duration, and we can also deal artificially, of course, with uncertainty in the critical path method by using this kind of buffers and floats, or buffers or floats. So if you have uncertainty, you can just allocate more buffers, which is kind of artificial because the nature of uncertainty is something that you cannot really predict. So the question is kind of paradoxical. How can you allocate buffer for something that you can't really predict? But this is one deficiency of the critical path method. What buffers are good for, however, is to shuffle resources around. So if you have a critical activity with no buffers, or with zero buffers, then you can shift some of the resources from tasks with a lot of float to it, and then hopefully speed up the whole process. We saw an example in the last lecture, and probably there would be a similar task required in the exam. All right. And the rest of the course is basically going to be about studying our solution. This should be just one question mark. This is not like a super existential question, but this is what the rest of the course is going to be about. Does the solution work? And if not, who is to blame? And I particularly like this lecture, today's lecture, because there's going to be an example precisely of this situation. The solution doesn't work, and two parties argue whom to blame. And they actually argue and settle this in court. And they use systems dynamics to do this, which is pretty amazing. They use modeling and stuff like this, which reminds me that today we're also going to be introduced to modeling. This system dynamics model that I talked about. You will not have to do any models for the self-study, not yet. But this is just a flavor of the models we're talking about, the so-called system-level models. We model the whole system, not the individual elements within it. All right. As I promised you last week, we're going to focus a little bit more on quality management. So quality. Last week we saw how time constraints can influence our project. Today we're going to see how quality constraints are going to influence our projects. And the quality, what is quality control in simple terms? In a kind of intuitive notion. What do you understand when somebody tells you, yeah, our project needs quality control? Yeah.
Measuring the outcome of the project against the objectives and goals that were set prior to the project's commencement.
Yes, that's true. And then what do you do after you measure the outcome?
After you, I'm from software background, so in software when you do quality control, you write down the observation or outcomes of your quality control, you do the unit testing of what you have expected as a result.
And if expectations don't match reality?
Then you have two options. You generally define the problem into one or two categories, one of which is it actually something that is required for your delivery as a solution, or is it something that is there as an issue and you can live with it, and or it's something like it is something that is like a critical part of the project, so you cannot really deliver it.
What if it's something that is needed, you need to deliver it, but it doesn't work as you expected?
Then you have to stop the delivery and you have to fix it.
Fix it is good enough. I was looking for the term go back and fix it. Because quality control is nothing more than a feedback loop. And today we're also going to be introduced to feedback loops, which is going to be expanded in next lectures, but quality control is simply a feedback loop. So at some point in your project, and what these points are is also going to be introduced, you check your expectations in terms of quality. If something doesn't work, you just go back and fix it. It's not as simple as that, of course. Sometimes you can't fix it. Sometimes you need to account for propagating changes along your project. But this is what quality control represents, a feedback loop, nothing more. So today, what we saw already is kind of a sequential approach to project scheduling, right? We saw the critical path method. We saw the how you can break a project into subtasks. And these subtasks were either sequential completely or fully concurrent, fully parallel, right? If you remember the critical path, you can have a whole chain of tasks which are fully sequential, or you can have two tasks which are completely concurrent, completely parallel, but nowhere in between. What this lecture is going to be about is the so-called multi-phase projects. Because you see, in every big project, you can't just split things into subtasks and blindly going through all the subtasks. If you build a garage, like we saw the example in last lecture, maybe you can do this. But if you have to build a tunnel which spans 15, 20 years, or if you have to produce some software product or a microchip, you need to do more than just splitting into activities and tasks, and you need to do these kind of phases. And here we're going to be talking about the project life cycle, which is nothing more than the human life cycle, right? As humans, you're born, you grow up, you're mature, eventually you decline. Well, you decline and eventually you die. And it's the same with the project. It's conceptualized, this is one phase, then it's designed, another phase, it's implemented, and then finally it's decommissioned. So these are the multi-phase projects, and we're going to see that things get complicated when you have multiple phases, each with a different task. And this picture hopefully illustrates the idea. So here we have a project which starts from, let's try to do that now, which starts from here and then finishes here. And we have multiple phases within this project. It's up to you to define the phases. Different industries have different standards for defining project phases. And within each phase, okay, I shouldn't use the pointer. Within each phase, we have a number of activities. So these are the activities that we talked about, right? For example, design phase. What do I need to do to design my product? The production phase, the same thing. And you can use the critical path or this kind of scheduling approaches within each phase. And let me introduce some terminology. We have the so-called upstream and downstream directions. It's similar to supply chain. When you go upstream, you go to the producers of raw materials. When you go downstream, you go to the customers. And here's the same thing. When you go upstream, you go to the beginning phases of the project. When you go downstream, you basically go to the decommissioning or getting the project out of the market. And here, quality control, this kind of feedback loops, can happen between phases, right? So let's say your production can spot some kind of design flaws which are only available or which are only known at production stage, and then you feed back these inputs back to design, or you can have quality control within each phase. It's pretty intuitive. There are going to be examples on this. However, these are what we call kind of unwanted feedbacks, right? Nobody wants to realize that at some point your quality or your project is delayed, and then you have to go back and fix something. And what people normally do, since this is kind of an unwanted thing, they fall into a certain mental traps. We're going to be talking about these mental traps, but in essence, it's the idea that you don't want to spend too much resources going back. So basically, you settle for something suboptimal, right? What you said. Do we really need this thing? If we don't really need it, then we just don't care about it, which is already a problem, because if you didn't really need it, then you shouldn't have put it in your milestone. In your milestones. But the point of this slide is that we can have feedback loops between phases and within a phase. All right. So how do we control for the success in terms of quality, in terms of time between different phases, and also within a phase? And probably the MAS students or also the master students with work experience, you already know that people like to use this idea of milestones, right? You can have milestones or checkpoints, as many as you want, basically. Of course, there is again a fine balance between having too many milestones, too much paperwork, too much administrative overhead, and too few milestones, which would basically leave a lot of deficiencies unspotted on time. But the milestone is simply a decision point. It's simply a checkpoint. And you can, for now, let's imagine we put the milestones between each phase, although this does not have to be the case. Two things happen at a milestone. You produce some report outlining what this milestone have achieved, or what this milestone has achieved, and then you make a decision based on this report, or deliverable. Here it's called deliverable, yes. And the decision, of course, may be, do I go back and fix something? Do I stop the project? Or do I just continue because my milestone is okay? And I think this idea is pretty intuitive. At each deliverable or each report that you present to your managers or to your stakeholders in the project would either consist of results, tangible results, like you've managed to implement some piece of software, you've managed to create a prototype of something, it works, or it consists of some intangible results, depending on what your milestone is, right? It could be you come up with an idea how to approach a problem, you come up with a concept, with a model, things like this. But the important thing is, again, you have to be able to evaluate your milestones, just like you have to be able to evaluate your solutions. How we do this? Of course, objectives. Objectives are very important. You can be as precise as your objectives are, not more. All right. So there are two ways, we're going to be looking at two ways to define milestones and to keep track of how the performance at each milestone. The first way is a very kind of visually appealing and intuitive way. It's this milestone trend diagram. So, has somebody ever worked with the milestone trend diagram? Have you ever seen this? No one, good. All right, the idea is pretty simple. Let's try to explain it with this thing now. So on the x-axis, right? So this here is the or let's say this here is the beginning of a project. This is time 0 or time 1, however you want to index that. This is the beginning of the project. And the x-axis are the reporting dates. Reporting dates meaning at each of these dates, so these are relative dates compared to the beginning of your project. So this is, let's say, 2 months after the beginning, 3 months after the beginning of the project, 4, 5, and so on. So at each reporting date, you ask yourself, how long is it going to take me to complete some milestone? Let's look at the green milestone, right? So in the beginning of your project, you ask the team, let's say the project team, how long is it going to take you to complete the green milestone? And then they say, well, it's going to take me 8 months after the beginning of the project. So if this is January, then 8 months would be August. Then you say, okay, fine, you record that thing as a point. 1 month later, you ask the project team again, how long is it going to take you now? You've been already 1 month into the project. And they tell you again, well, it's going to take me 8 months. I will finish again in August. The estimate holds. And then so on, 3 months, 7 or 6 months. After 6 months, you ask them, how long is it going to take you to complete the project? They tell you, well, 8 months, everything is fine. Right? You see already that this is a good thing. The estimate never changed. So you are always on schedule. You didn't uncover or you didn't discover some kind of quality problems, time delays, unexpected consequences, things like this. So this is a good thing. Now let's look here. You can already see that the revision of the estimated time needed to complete the black milestone increases as the project continues. So basically, when you ask the project team, how long is it going to, in the 4th month, how long is it going to take you? Well, it's going to take me now 4 months, almost 5 months. Even though in the beginning I told you it's going to take me 3 months, right? So this is an example where a project is being delayed, has quality problems, and things like this, which cause this shift in time. And the good case here is, well, we're going to see if that's really a good case, but basically this is the opposite thing, right? So you ask the team, and they constantly revise their schedule in a way that now your project takes less time. Is that clear? It's pretty intuitive, right? If it's clear, then can you tell me why there can never be any points in this half? In the lower half. Hmm? Only after day 3. Yes, basically that's the reason. If for at some point you find a point here, this means that either for you time is going backwards somehow, or your project is out of date. So you ask, let's say in the 8th month, you ask some team, and they tell you, well, it's going to take me 5 months after the start of the project to finish that milestone, which means that this estimation is out of date. All right. This was the milestone trend diagram. It's pretty intuitive. It's very simple. You can really spot delays as they appear. Of course, this depends on the granularity of your milestones, which brings me back to the point that too fine milestones can allow you to spot delays or quality problems almost in real time, but it will generate way too much administrative overhead. So you have to find a trade-off. If you just have 2 milestones in the beginning and at the end of the project, you will probably never spot any problems. It forces people to be disciplined, which may be or may not be a good thing depending on the culture of your company, of course. I would imagine, I think that's similar to this Scrum methodology in software development, where you kind of force people to come up with not exact, but quite reasonable estimates on how long they're going to need to complete a certain piece of work. Well, this is the same thing, basically. You ask them constantly to revise their estimations. And it kind of forces people and project teams to be more disciplined in their time management. But of course, again, this could be a negative thing. you need to yourself, like the person doing this or the manager doing this, you need to be disciplined yourself because you have to collect all this data somehow. You have to constantly update it. So I find this, or maybe that's the reason why this approach is not used so much, because it really requires a lot of discipline from all the parties involved. But again, if you have experiences, please bring them forward. Another thing that you need to do in order for this trend diagram to work is you have to be aware that if there is a delay in the project, you spot a delay, you know that you have to go back and fix something. But this is much easier said than done, because going back and fixing something involves feedback loops. So maybe the fix that you need to do is contingent on something else that needs to be changed more upstream. So you need to have an idea of how different feedback loops influence each other in your project. We're going to see how this is modeled. But the conventional project management approaches tend to ignore this kind of simultaneously operating feedback loops. All right, another way to keep track of our success or the milestone success is this so-called integrated cost and date control. The idea is also simple. You have a kind of a, in this case, it's a two-dimensional space with your important dimensions that you care about. For example, here we care about time and costs, but of course you can add as many dimensions as you want. This basically defines what success means to you, what successful milestone means for you, and of course, you put each milestone in this space, right? For example, here we have a milestone which took more time to complete and it cost more to complete. So that you can clearly say, well, that's a negative thing. Depending on how you weight the different dimensions, you can basically have positive or negative effects attributed to tasks which violate one of these two dimensions. Here we weight date, or we weight time and costs equally. So if you have a task which fell short on one of the dimensions but made up for it in another dimension, we kind of say that this is neutral, right? It took more time to complete in this case, but it cost us less. So all in all, it's a neutral case. Of course, this depends entirely on how you weight time and cost. And in most cases, this is not true. The same thing for here, right? You needed more money to complete your milestone, but it took you less time. Here we have the positive case where it took you less money and less time than planned. Is this really positive though? Yes.
It means you did a mistake in the planning.
I wouldn't call it a mistake, although this may be the case, but I wouldn't like to call it a mistake. Yes.
I think it's always good you are on plan. I mean, it's what you plan at the beginning, it's improved when, at the end of the project. It's the same regarding to cost, regarding to time. In that case, you estimated a bit bad with a positive meaning.
Positive meaning. Can you define that?
At the end, you didn't lose. You didn't. You saved money. You saved time. But actually, you did a bad project plan at the beginning.
So would you say this, would we put such a milestone, or would we say it's a positive, negative, neutral? What would you say?
It depends on which, how do you look at this? I mean, from which perspective? But from perspective of project planning, it's actually negative.
I agree. It is negative not because Not only because you maybe made a mistake, which of course can happen, but it can also be negative on a different level. It could be, imagine you talk to your customer, and then your customer, after you deliver, your customer sees that you deliver earlier, and it took you less money than planned. So what would the customer think? They would think, well, do you really know how to schedule your projects? This time it took you a lot less in both dimensions, but next time maybe it will take you a lot more. Furthermore, did you do it intentionally? You know, did you just try to sell success later on, right? By estimating more time, more money, and then sell me this success, which was actually not a success really. It was just kind of an overestimation from your side in the beginning. So I find this as a kind of a negative thing to have. Even though you may not deliver to an outside customer, even though you may deliver only within your own organization, this is still, I think, a bad case. When you intentionally or unintentionally underestimate or overestimate the requirements.
Depends how you communicate this to the customer actually, because you can't see in the future. You do an estimation and you realize, okay, we can implement it in another way. During the implementation, not during the planning. You can.
Yes, that's true. That is true. But the thing is, normally, when you have a multiple phase project, so let's say your customer wants a microchip from your side, right? Of course, you kind of constantly revise the schedule, but at some point at the end, let's say shipping, right? Just the shipping needs to be done. This is kind of a self-sufficient phase. So you can even think that this is the end phase of your contract with the customer. Shipping is something that you can more or less estimate the costs and the time needed to ship the product. For instance, I can give you an example. I recently, well, actually not recently, and that's the problem. I ordered a laptop from Neptune, as probably many of you have done so. But now it's been 1 month, I haven't got this laptop, and it's probably going to be at least half a month until I get it, because they have problems with the shipping. So in that case, you can say that they're somewhere here, right? So this is actually an example going to, not to this point, but to the point that you can still estimate the end phase with your customer. All right. So I wouldn't say this is a positive thing at all. Maybe, yeah.
I think it's generally positive because you do an estimation on the project schedule, if you're ahead of schedule, and if you're ahead of estimated cost, generally it's positive, I guess. Because you assume you do the proper project planning. So you're ahead of this.
Then your assumption may not be so right after all.
Yes, but if you say you understand the project on different sites, for example, and in this case you are faster and you have use less cost, it's positive. Generally, I agree on this line.
You agree that this is positive? Yes.
My experiences in project management, you never can plan a project that it's finally on time. You always have some deviation.
Of course.
And this, if this is the final point, the finish point, then it might have a negative aspect. But this might be just one milestone.
Of course,
and
yes.
you have many others. And if you have such a point, you might also have some negative milestones, and you can reallocate resources from this positive point. So finally, it's positive. That's my experience in practice.
It's true. But for this case, maybe, let's say, it's the result of one project. So we planned the project, and then we allocated the resources, all resources for this project. And we maybe have stopped other projects or other tasks. So in that case, we planned actually not good. The result is good, but
You never can
it's
plan.
from the
so
project planning point of view. It's I mean, at the end you have to actually resources must be appropriate.
I agree. This is actually a good point, and you're right in the sense that if this is an end phase of your project, like the very end thing that you do, then this reasoning applies, right? But if it's the beginning, obviously, it's not. You can make up for this, or you can revise your project scheduling. So at the end, it may even be a positive thing. But I do think that if that's the only phase in your project, it's a very simple project. Let's say, can you write a simple program for me, and I'll pay you something. And then you say, well, I'm going to need 1 month, and it's going to cost me 1,000 francs, and then it takes you a week, and it costs you 100 francs. Then
You still can postpone the delivery.
of course, that's what people do, exactly. True.
That's the truth.
Yes.
Another way, what would be, in your opinion, the positive point? Because as you said, it's negative. There's no neutral and negative. There's no positive anymore.
I would say the positive is here, but of course you can never. Well, no, it's not binary. Things can never be either completely positive or completely negative, right? So this could be, even if it's slightly here, it may be positive. You know, it contextual completely, of course. All right, but I just wanted to bring up this point with project scheduling, that sometimes doing, or let's say performing much better than what you projected, also needs attention. So you need to revise the way you estimate things. Finally, the final thing with the project management approach is these control gates. So basically at the milestone, you take a decision: should I continue or should I stop with the project? I did not fulfill my milestone, the quality is bad, I will not fit in the total project estimated time, so what do? Do we stop the project? Or for instance, you suddenly realize that your project has lost its market, its target market, like the chip you are manufacturing cannot be sold now because it would be too big for the market, and you only find this out after the production phase, for instance. So what do? You stop the project, or you go back and you change something. And it really has to do with resources. Lots of time, you don't have enough resources to go back and to change your project. So what normally happens, what ideally should happen is you should kind of stop the project. But what normally happens, people just go with it anyway, right? And hope that the laptop they've produced will still sell somehow, even though it's much heavier than everybody else's laptops, right? However, if you have enough resources in terms of, let's say, time, in terms of money mostly, to go back in to change something, then this is the kind of a mental trap that I'm going to. What happens is, remember the problem-solving saga. You had numerous solution approaches. Let's say you selected some of the better ones, the best one, whatever that means. Now, when you go back, you need to make a choice. Do I explore new alternatives? So do I find new ways to produce this microchip so that it's smaller or less power, more power efficient? Or do I settle for kind of a suboptimal design? Right? So if you have to explore new alternatives, that would cost even more money. However, if you don't, if you just say, well, let's go back and take one of the solution candidates that we had before, this would actually cost you less money compared to what you've already invested, but you would end up with a suboptimal solution. And in these situations, people tend to attribute extra credit to these suboptimal solutions in retrospect, right? So they go back and they think, well, this solution was not that bad after all. Maybe we should have chosen it the first time, so it's cheaper, and it's going to take us less time to implement, and maybe the problem with more power or more DPM, defects per million, is not such a big thing. We didn't estimate correctly the negative parts of this solution. So probably it will work out fine. So you settle for you don't really settle actually. You convince yourself that this suboptimal solution is good, is better, at least better than you originally thought, and you do it, and then you end up with something which is actually even more disastrous than if you had just stopped the project initially. So this is the way we call it here a mental trap in a sense. It's something that you have to be aware of. If you ever go back and you try to change something in your project and you find yourself attributing more weight or more credit to these solutions that initially you disregarded, then you're falling into this trap, and it's kind of dangerous. And due to this, I mean, why is this the case? Obviously, you've invested a lot of resources in your project so far, and your ability, this graph shows is, your ability to change the project is a lot less than in the beginning. So your freedom is a lot less. What you can do is you can either invest a lot to change the whole project, or you just invest a little bit and you settle with a suboptimal solution. What this shows you is kind of a abstract way of the relationship between your freedom of change and the progress of your project. So we have, as time goes, okay, this is just one phase, the development phase, but of course it could be any phase. As time goes, your knowledge about the system increases, right? Here you have only basic assumptions, basic cost estimates, basic resource estimates, and then your knowledge about the system increases. Now it's going to cost you more, it's going to take you more time, maybe I'll be late at the end, but your freedom at the end to change something is a lot less, because you've already invested a lot in the project, and this is what we call path dependence. More on this in the coming lectures, but you know, I think this is pretty intuitive, right? It's only conceptual. For instance, if at the end of your, if during the writing of your master thesis, you suddenly realize that you didn't want to study physics, you wanted to study French literature, right? It's too difficult, it's too hard to change. The freedom that you can do is, yeah, maybe you can read a few French books, but you have to complete your master thesis. Again, the other option is to invest a lot of resources, ditch completely everything you've done so far, and start studying French literature. And people do that, actually. They just suddenly realize that they wanted to do something else completely. Actually, a former professor of mine used to kind of bring to our attention this potential conflict. So hopefully he mentioned this in the beginning, right? So if you don't want to study, if you're not sure you want to study this, maybe you should change, which is a good advice actually, but not a good advice if it's at the end. All right. So I mentioned that quality control and also checking your milestones, going back and changing something, is nothing more than a feedback loop. This is the technical term. Okay, I have to speed up a little bit. And what is a feedback loop? I think most of you, especially the engineers around you, are painfully familiar with feedback loops, especially the electrical engineers. But what feedback loop is a very simple concept. You have a certain input which goes to your system. You take some of the output, say you take your milestone, and you compare it to something that you expected. If this is not what you expected, you change your input, right? And an example could be with this heating a room, right? You want 21 degrees, for instance. Obviously now I want a little bit less, but if you want 21 degrees and you measure, let's say, 30 degrees, then you have to decrease your heating system. Next time you measure, maybe it's 19 degrees. It's too few, it's too little, so you have to increase. All right, so let's continue after the break. Yes. All right, let's continue. Let me just set my timer here. So I told you about the feedback loops, what the feedback loop actually is. In our course, let's say in judging how this kind of going back and fixing attitude, how it affects your system, will distinguish between negative feedback loops and positive feedback loops. Without going into technicalities, in engineering, for instance, a negative feedback loop is something, going back and fixing something, is what brings you to a balance, to an equilibrium kind of state, right? So you go back and you balance your input in a way that your output, goes to the value or to the milestone that you expected, right? For instance, you set a quality standard. A negative feedback loop would be, you go back, you fix something in your process so that this quality standard can be achieved, right? A simple example again is the heating system, where you constantly try to bring the output to the desired temperature. This is a negative feedback loop, and other examples are, let's say, the standard supply and demand idea, or the interrelationship between supply and demand in economics, for instance, right? If for some reason supply increases, then the price would go down and demand would increase as well. There would be a new equilibrium point. So this is this kind of a negative feedback idea. By the way, the human homeostasis works in the same way, right? The way that your body regulates its temperature, it works in exactly the same way. You have a question? Oh, okay. Right, if you get too hot, then your body emits sweat. If you get too cold, then blood vessels close and temperature is preserved in your system, which is actually pretty good. Now, positive feedback loops, it's kind of a terminology mix-up, because in reality, negative feedback is good. It's positive in a sense, but positive feedback loops are bad. Positive feedback loops lead to exploding behavior in your system. This explosion can go, you can explode a certain value or you can decrease it to zero, but it's basically driving you away from equilibrium. Okay? All the bubbles are positive feedback loops. Self-fulfilling expectations are positive feedback loops, right? You expect the house prices to go up, therefore you buy houses so that you can sell them at a higher price later on, but buying houses causes the price to go up again, and then it goes up and up and up. Eventually, people realize this inflation and everything crashes, right? So these are positive feedback loops. But also, it doesn't have to be as abstract as this. If you take a microphone and you go next to a loudspeaker, even if you don't talk, you would get this squeaking noise, right? Because the random noise, which is not perceived by you, gets amplified by the microphone, comes out amplified from the speaker, gets picked up by the microphone again, gets amplified even more, gets picked up again, and then in a couple of milliseconds you have this explosion. So these are the positive feedback loops. And I would say, unfortunately, in big projects, each negative feedback loop that you want to establish in order to fix something is accompanied by a positive feedback loop, which destabilizes your system. We're going to see an example of this, but keep it in mind. Because what managers want to do is they constantly try to implement these negative feedback loops, but they sometimes don't know, or they overlook the positive feedback loops, which actually can more than offset the gains from the negative feedback. And going back to this idea of feedback in general, I just want to show you the different kind of, let's say, the span of different feedbacks that you can have. Here we talk about quality feedback loops again, but imagine the following, right? Let's say this is our, this is our typical problem-solving cycle. Yes, it's basically a problem-solving cycle. So you set your objective, you come up with solution approaches, and then you implement this whatever solution, and this is the end of the project, right? So this could be just one little phase of your project. It could be just one little task in your project, like produce whatever software library. So what happens is at the end, or at some point of your project, you have a milestone defined, right? And then you compare, you control in a sense. Is the current output in this current time of the project phase or activity, is it what I expected? No. If it's not, well, then maybe this one is a bit better. This is the blue feedback loop. If not, then we need to change something. The project management task is to change something, to take corresponding measures. For instance, you see that you're going to be delayed, your project is going to be delayed, so measures could be you make people work overtime, for instance, or you hire more people to do the job faster, so that at the end you can be on time. But so this is changes, feedback loops within your project, within your whatever the project may be. It may be an activity or whatever, right? So within your project. But there are also feedback loops that go out of the project, and the idea is the following. So here again you do your controlling, you see that something is wrong, but now what is wrong is not project specific. Maybe what is wrong is the feasibility of your whole project. You know, this is the idea. Does it make sense to continue with that project anymore? Maybe it will be outdated by the time I've finished with it, and I won't be able to sell it, for instance. So what you need to do, there's nothing you can do in project management. There's no overtime or more workers than you can hire. You need to go back to your planning stage, and you need to ask yourself the question, well, does this project make sense now? If yes, what do we change in the goals of the project, in the aims of the project? So you go back to the very, very beginning, right? You realize you cannot sell this microchip because it's going to be too big. There's nothing you can do about it. You go back to the beginning and you design a smaller microchip. And then you go again in implementing this smaller microchip. So these are these two different scopes of your feedback loops within the project itself. So incremental improvements, you might say, and those that span, let's say, the environment, right? You estimate the feasibility of your project or the aims of the project, whether they still make sense. And now, as I promised you in the first lecture, we'll deal with these kind of small changes here, right? You need to constantly change something due to various reasons. Your customer wants you to change something. You realize that you need to change something. So, in other words, this one. In large-scale project management, for instance, yes, the tunnel, the Gotthard rail tunnel, right? It's a huge project. I think it's going to be completed 2015 or 2016 or something. It's going to be open for use. I think it started in 1991 or something. So it's a huge project. And you can imagine that in these big projects, even if everything goes according to plan and your customer doesn't want any changes to be done, there are still things happening that you cannot control. New technology is being developed. New regulation standards are being established. So suddenly, your project needs to be, let's say, more environmental friendly. And you only realize this when you're in the middle of that project. Or let's say your customer wants to incorporate a new technology, like in the example we're going to see. So this kind of small, I mean, if you compare it to the scope and to the resources of the project, these kind of small changes, what is the effect of these small changes on the project? And the example that we're going to see is going to illustrate perfectly these small changes in court. So the question is, these small changes that you do, and sometimes there is no other way, but you have to do them, right? Even though everything is fine, new technology comes available and so on, do they add up and result linearly? Do they add up linearly and result in small impact, overall small impact? Or do they add up through these feedback loops? And do they propagate and add up in a complicated, nonlinear way that eventually results in the project cancellation? Right? So what is the impact of these small changes given these large-scale projects? And what is important also to realize is that these small changes are unavoidable in large-scale projects. They're simply things that you can't control in life. Yes, so this is really a scientific question at the end of the day. It's not just a minor concern. We really need to know the role of small changes. And the example, the running example for this lecture, one of the two running examples, is the case with the shipbuilding company, Ingold Shipbuilding. So basically what happened is, and just in your notes you have a reference to a book where this example was taken from. I will post the chapter of the book that deals with this, so there's a lot more information, legal information, all this kind of stuff about the settings. But what happened is that this company, they won a contract from the US Navy in the beginning of the 70s to build these ships, like 30 destroyers and 9 carriers. And that was a big deal at the time. You know that in the US a lot of money are spent on defense, and there was a lot of money involved in this project. In fact, these were the only 2 projects, I think 2 of the 4 projects that this company was working on, and all of the projects were from the US Navy. Right? So this was a big thing for them. And the scope of this project was so huge that they had to double their workforce. At the end, they had 20,000 people working on building 30 destroyers and 9 carriers. I mean, 20,000 people. It's a huge amount of workers. And what happened when, I don't remember exactly the time, but I think the estimated time was about 15 years or something to build these things. What happened is the US Navy, being the customer, they constantly requested new technologies to be incorporated. They always wanted to have the latest GPS tracking ability and whatnot in their ships. So as new technology became available, they went back to the Ingold manufacturer, to the Ingold shipbuilding, and they requested these changes. At the end of the day, what happened is that the projected cost overrun was in the scope of $500 million US. And just to put this number into perspective, the annual turnover of this company was in about the same range, in the same ballpark, right? So basically, they would need, just to cover this project, they would need, let's say, the same amount of money as their total turnover for 1 year. Not profit, but turnover. So it was a big, big, big cost overrun, which of course generated a conflict between the shipbuilding company and the US Navy. As you may imagine, the shipbuilders, they claimed that all these small changes caused a lot of feedback loops in upstream. They caused a lot of unexpected delays, and eventually they resulted in this $500 million cost overrun. The US Navy, on the other hand, they took the opposite position. They said, well, these are just small changes within a given task, so we're willing to pay whatever this kind of overwork for employees might have cost, the direct costs, but this in no way can be in the range of 500 million. Right? These were just small changes, and basically the company is at fault because they have bad project management. They don't allow enough buffers for their tasks, so if there is some delay, they cannot handle this, so it's bad project management on their side. And what happened is actually the shipbuilding company, they sued the US Navy. And since they're the plaintiff, they had to prove actually in court that these small changes were the resulted in this huge cost overrun. So they had to prove this. They hired a consulting company to model this whole process of building a ship, right? And basically, there's this conventional model. The way that the shipbuilding company was estimating the effect of these small changes and all this kind of stuff was done without taking into consideration any feedback loops, any propagating or rippling effects from a small change. And this consulting company, they developed a system dynamics model. It's here. They develop a system dynamics model which takes into account all these interrelationships between different tasks, especially feedback loops, right? And what happened at the end was they had this model. They could prove that these kind of small changes could result in a big overall impact. Then the shipbuilding company went to the US Navy, presented the model, and basically this was as a proof that the US Navy was at fault. The US Navy, in fact, inspected this model, and I mean scrutinized the model really. They came up with some criticism for the methodology, for the estimations of the costs of the different changes, different tasks, and so on. And they expected that these modifications would greatly reduce the impact of the small changes. But when the shipbuilding company implemented these critics, the overall impact was actually higher. All right? So the US Navy did not expect that by decreasing the cost of some of the tasks, they would actually get a higher impact. And at the end, actually, I just noticed yesterday that somewhere in your notes it says that the shipbuilding company won a lawsuit. There was no lawsuit at the end. They settled outside of court. And they settled for $450 million out of 500, which is almost everything. Right? So there was I found this out because I wanted to find the court cases. You know, they're public, so I wanted to find them. But I couldn't find them. At the end, it turns out that they settled outside of court. Okay. So I will introduce this system dynamics model that these consultants developed. Before doing that, there are a few kind of entities that exist in that model, or structures, as you might call them. We distinguish between the following kind of activities. Not activities, but entities. Entities, I guess, is the right word. We have work to be done, right? So this is the work that needs to be done. You can estimate it in different ways. That's not so important. But there is an entity called work to be done. For instance, if I'm an important bureaucrat and I have to put stamps on a paper, right? The work to be done may be this pile of paper here that I need to stamp. The work being done here, the work being done is the actual paper that I'm putting a stamp on. So this is the work that is currently in process. The work really done is the completed work which has passed quality standards. Yeah, so this is where quality comes into play, right? You can imagine, you can immediately see that this model incorporates this kind of quality concerns at every unit of work. And it turns out, I mean, these consultants also did some empirical work later on. They found out that the work really done the first time in the industry is 68%. So 70% of all the work is really done in a quality way the first time. No need for feedback. But in the military projects, it's appalling. It's 35%. So it's a huge, I mean, as you might expect, I guess, it's a huge, deficiency in this kind of military project. And so what happens once you realize that your work done does not conform to quality standards, then the question is, okay, what needs to be changed? And the thing that needs to be changed is the work, it's referred here as the undiscovered rework. So now you know that you have to do something which you didn't know before the quality check. again, before going into the details of the model, let me introduce in a more kind of system dynamics perspective how these models look like in general. What the entities that we're going to be working with, and eventually you'll have to simulate this in your self-studies, are called basically stocks and flows. Stocks, this is a stock, right? Stock is something, is basically an entity or quantity which accumulates value over time, right? The work to be done is a stock because it accumulates over time. As more work becomes available, it's a stock variable or it's a stock quantity. The rate of change of this stock quantity is called a flow. So if you have the work to be done as a stock variable, the work which is currently being done, so the work which is taken out of the stock variable and currently being processed, like the sheet of paper that I take to put a stamp on, is called a flow because it reduces your stock variable. In the same way, the work which goes, for example, I put my sheet of paper on the work done stock variable. This would be called also a flow because it increases the corresponding stock variable. So we work with stock and flows, and this is called inflow and outflow. It's pretty intuitive, right? So for example, the flow of materials, like the flow of papers that I get, is a flow variable. This could be the pile of processed papers, or let's say this could be this is the work to be done. This is the papers that come to me for stamping, and this is, somebody is constantly replenishing this pile of papers that I have to work on, right? So like citizens giving me bureaucratic things to do. All right, we can put this whole model into equations. I mean, that's how they express them in system dynamics. The stock variable here, the change of the value of the stock variable at any point of time is simply the total sum of all the inflows and all the outflows up to this time, right? So this is don't be intimidated by this kind of equations. You will not have to produce these kind of equations in the exam, although it will help. Yes.
The work really done, what would be, I don't know, being done or really done, what would be the outflow?
The work really done.
I don't know, really done or being done.
It depends on how you structure your project. If you have the work really done, what do you do with it? That's the question. Maybe you give it to somebody else for further processing. Maybe you send these pieces of paper by email, by mail to people. So it depends what your project is.
An outflow could be considered a mistake done and that you thought that you have done something wrong.
Yes, for sure. If you have a stock variable which is called work done, but not checked for quality, and if you discover a mistake in this, when you check for quality, you discover some task was done wrong, then of course this outflow, you take this task, you put it to another stock variable which may be called work to be redone, right? Because it's a faulty thing. So this would also be an outflow. So yes, discovered mistakes could also be an outflow. It's all conceptual. I mean, it's all up to you how you define your stocks and your flows. But this is the idea. If something accumulates over time, it's a stock. If it's just a temporal or instantaneous flow, it's kind of a double definition, but you got the point. So the stock is simply the net sum of the net difference between everything that goes into a stock and that goes out of the stock, and you sum this. Basically, integral is just a sum. You sum this over all the preceding time. And of course, we have some starting value for the stock, right? In some cases, your stock variable, your work to be done already exists when you got the project. If you're that unfortunate project manager. All right. So this is the integral way to describe this, by a sum. You can also describe it in a differential way. And the question here is, how does my stock change with time? Before the question was, what is the total value of the stock at this given time? Now the question is, how does it change with time? Well, it's much simpler. There are no integrals. At any given point of time, the change in your stock would be the difference between what goes in and what comes out. Okay? All right. So with this in mind, that is the basic concept of the system dynamics model that these consultants developed. Of course, the whole model it's completely out of scope of this lecture, and even in the book you can't find the whole model. I have uploaded a paper in the literature section today, which is written by one of the consultants working on this project. There you can find more details about the model in terms of more real-life examples not real-life examples, but more kind of quantitative details regarding all the entities here. If you want to read it, of course, you're welcome to do so. But the important point is to understand the concept. And the concept is the following. As I mentioned, this guy said the following. Well, let's model the work to be done as a stock variable, right? So this is a stock. We have a work to be done in any project. We also have the work really done. So what is the difference between work to be done and work really done? Well, that's the quality check that you do, right? This is the basic feedback loop. You have something that needs to be done, you do it, right? You do it here, work being done, I put a stamp on the paper, and then somebody checks whether this stamp was aligned correctly, for instance. If that's the case, then my other stock variable, work really done, increases by whatever amount. If that's not the case, however, if something doesn't work, then you put it in a stock variable which is called, doesn't work. You don't know why, it just doesn't work. You take this stock variable, then maybe somebody else takes the stock variable, some other team, and they discover what is the problem with this thing, what needs to be changed. And they put it in a stock variable called known rework. So this is work which does not conform to quality standards, and you know how to fix it, right? This is work which does not conform, you don't know how to fix it. And then again, the known rework goes back to the process of work being done. So it's kind of another inflow that goes to the quality check later on, right? This is clear. So you see the feedback loop. This is the feedback loop, the quality feedback loop that we talked about here. But now what is interesting to see is that you have work which is really being done. You have built 1, or let's say 10 meters of your tunnel, or you've produced 5 libraries of your software product, and then suddenly your customer comes and says, well, I want you to change this. I want now my product to have this latest GPS tracking capabilities, for instance. What happens is you take some of the work which is really done, and you need to change that, right, to incorporate the customer changes, which goes back to the stock variable known rework. So it's not defect per se, but it still needs to be changed in some way. And then it goes here. So this is the second feedback loop, this one, which is entirely due to customer changes here. All right. And basically the bullet points are everything that I said so far. Therefore, I think it would be easier. So basically this slide explains that diagram. And I think it would be easier to just start with that diagram, and only later on for your own reference you can refer to this slide. But this is a more detailed example of the system dynamics model that they developed. And at this point, let me just remind you what the system dynamics model is. You model the whole system, right? You don't model the individual interactions between, people or between project managers. You model your whole system from kind of a bird's eye perspective. So here we have the typical, the familiar stock variables, work to be done, non-rework, and so on. Now, what happens? I think it would be easier to remove this. What happens if your customer comes and requests small changes from you, or some changes. Let's say I wanted to incorporate this new functionality because this is getting popular nowadays. It will be important in 15 years. So what happens is, well, you try to create these so-called negative feedback loops. And in other words, you try to fulfill these requests, right? So what happens is, well, you hire more people, right? This is one thing that managers can do. You hire more people so they can work more, and they will kind of finish, they will be able to do this additional work at the same time. So you hire more people here. This would affect, don't worry about the technical term for people. You will see this, but for now, just remember stock flows and we have people here. So you hire more people, and this will obviously increase the work being done. Right, this is intuitive. What you can also do, however, is you can make the current people, or the current workforce to work more, to do some overtime. All right, again, well, you know the 90-hour week mentality in one of the companies in Silicon Valley when it was being established. Right, so you ask your people to work more, and again, this would affect the work currently being done. Another thing that you can do as a manager, well, you can accelerate the schedule, which would hopefully increase the productivity of your people. And then again, it increases the work being done. So you try to, of course, these are just examples. In the real model, they had different things. But you see how you try to make some project management changes which bring you closer to the goal that you want to achieve. These are the negative feedback loops. But as I told you, each negative feedback loop is accompanied by a positive feedback loop, which destabilizes the whole system. For instance, you hire more people. Maybe in your vicinity of your company, the skilled workforce is not that prevalent. So you end up hiring less quality people. Right, the average employee skill goes down, so these are the dotted lines, these are the positive feedback loops, which would affect your productivity in the mid to long term. I mean, what do you do with these people if they're not as skilled as your hiring standards? What do you do with them? Maybe their work that they're actually doing is not as good. So you would increase that feedback here, the quality feedback. So this is one example. You ask people to work overtime. What may happen is they get tired, they burn out, suddenly some of your best people start to leave the company, they go to the competitors. So this, again, this would affect your productivity, right? Another example is you accelerate the schedule. Basically, you ask people to do more things in parallel, for instance, which causes congestion, people waiting to use the same machine, for instance, coordination problems, obviously. If things now need to be done in parallel, then they have to be coordinated, all this kind of stuff. And it causes also morale problems. Like, obviously, people get demotivated. So you see, these are just examples of a positive feedback loop which accompanies each negative feedback loop. And in the system dynamics model that these guys developed, they had these things incorporated. So by doing this, as I told you, they were able to prove to the US Navy that these small changes resulted in unexpected, unintended consequences, which is one of the characteristics of complex systems. When we try to influence a complex system, there are unintended consequences that sometimes, even with the best efforts, we cannot predict. But there is still a lot we can do. There is still a lot we can predict by trying to think about these kind of feedback loops, positive and negative feedback loops. Lessons learned from these examples is that small changes can ripple down or ripple across your whole project, all the phases, and result in big delays, Yes, so basically I've said all this. We tend to neglect the indirect effects. We tend to neglect them because, first of all, obviously they're more difficult to spot. They take more time to spot. So we just simply tend to ignore them. These were the effect of small changes. Now, I need to speed up a bit. Now, we come up to another optimization kind of technique. So far, we've dealt primarily with either fully sequential tasks, fully sequential also in the project phases. We saw one phase follows another phase, from upstream to downstream. The critical path method assumes sequentiality or full concurrency. But what if all these different phases, conceptualization, design, development, and decommissioning of your project, for instance, all these phases, they don't need to be sequential. And in fact, this goes into the direction of concurrent development. Some of you may be familiar with this. So you do part of the design phase at the same time with let's say, part of the production work needed. Right? So these different phases do not need to happen sequentially. And this is this idea of cross-function or concurrent development, where you basically try to study the network of your phases. So the phases, actually I should go like this. The different phases in your project are not sequential, but they're kind of assembled in a network. So some of them can be done in concurrency, in a concurrent way, in parallel. So imagine, yes, we have the product definition, the design, and the product testing and quality control phases, for instance. And these guys, I think, yes, you can find the paper of these guys in the literature section, but they propose the following thing. Maybe that would be easier to see. They said, well, no matter how many phases, so this was the goal, remember, we need to study how the different phases in your project can be done concurrently, and to what extent they can be done concurrently, and also which projects in types of industries and stuff like this can be done concurrently. So they said, well, no matter how many project phases we have, of course it's up to you as a project manager, it's up to your industry to define different phases that you need to do. But within each phase, we have more or less the following, they call them subsystems, or let's say different categories of tasks that you need to do within each subsystem, within each phase. And here they've talked about, they name this process structure phase. So this is a phase where you basically think about what work needs to be done in this phase. Like if it's a design phase, you think about, well, what do designers need to do? If that's a production phase, what do the manufacturing guys need to do? Then you have a kind of a category or a subsystem which is called resources. So these are the available resources. You have the scope of that phase. What is the scope of your design? You just want to design whatever product. And you have your quality mostly quality targets, but also, of course, time targets and budget targets. And all of these different subsystems affect the actual performance of that phase. The actual performance in terms of cycle time, defect rate, and cost. Cycle time is basically how many times you have to go back. Ignore the feedbacks for now. The point is here that each of these subsystems affect the performance in a direct way. For instance, the available resources affect your performance because, of course, the resources are limited. So you can only do your project, or you can only accomplish that phase in that time. You cannot do it any faster because you just don't have enough resources. Like for instance, so each of these subsystems affect the performance in a direct way, but also the different subsystems affect each other. For instance, the work that needs to be done in that phase generates demand for resources. Right? This is how you affect the resources. If you need to to design, let's say, a DRAM memory, the resources you need are a lot less than if you need to design a GPU latest generation, for instance. Right? So the different subsystems affect each other, and yeah, that's the most important thing. Let's see, do I need to go through that? Yes, quickly, actually. So these are the different phases that you can have in your project. For instance, you can have product definition, design, prototype testing, and quality control. And this is basically the multi-phase projects. Each phase influences each other directly. And by influence, I mean depend on each other. For example, prototyping, of course, you need to have a design already in place. And of course, you need to have some kind of product definition. Sometimes even without design, you can do some testing, you can do some prototypes only with having the product definition. But also, the quality loop comes into play. If something doesn't work here, then you need to go back and you need to change something in your design, and so on. So this is this feedback, actually. This feedback is what we don't like, right? We never like to go back and to change something. And this is what it's called, the feedback corruption, in a sense. All right, let's see now. So these guys, they focused only on the work that needs to be done in a given phase. They focused only on this work and they tried to model it in a system dynamics way. And they did this. So what we have here are all the tasks which are not completed, that needs to be done, so all the design work that you need to do. They're completed at some rate, and they go to another stock variable, which is called tasks completed but not checked. Then you check the tasks for quality. This is the quality loop here. If the quality is fine, then they move to the tasks which are approved, and then finally you release the tasks for the next phases, or for the next, for the next phases most likely, right? So this is the idea we already saw. Now I will move to the important stuff. This is just that picture put in a different way. I will skip that because we're running out of time. But back to the original question. How much of your different phases can be done concurrently? And not only can different phases be done concurrently, but the work within each phase, so the design work, for instance, in the design phase, it can be done, so different activities there can be done concurrently as well. And these guys came up with the following way to visualize that. Here we have % of the work which is done, and it passes quality control. Here. Here we have % which is done and passes quality control, plus what is available for completion. For instance, if you have let's say a software product, and this is, in fact, this curve is an example. If you have a software product, in fact, this is an example from a software product. In that particular example, it was split in different blocks. You know, normally you don't do the big software projects at one time. They're split in different blocks. And ideally, all the blocks can be done concurrently in parallel, right? This is the design phase or the implementation phase. All of them could be done concurrently. This is the ideal phase. The most non-ideal case is when they have to be done in sequence. In that particular case, they needed to do 20% of the blocks, of the software blocks, 20%, before they can parallelize all the others, right? So unless you complete 20% of the work, you cannot do anything else. All the others have to wait. All the other 80% have to wait. This is what is illustrated here. Unless you do 20% of the work, this is 20%. The work which is available for you to do is, so the work which is available for you to do plus the work which is already being done is just, again, 20%, right? You understand that? You start at 0. For instance, you haven't done anything. What is the work available for you to do? It's not 100%, it's just 20%. I just want to finish with that slide, which is one of the last slides, And we'll talk about these slides in the self-study, actually. I will explain them in more details, but this is actually a very, very nice slide. What it shows you is, now these are different phases of your project. And you know that different phases can be done concurrently. Let's say the design phase can be done, some of it can be done concurrently with the production phase. So what these guys did, they asked the designer in the design phase, they asked the design manager again in the design phase, they asked the product architect and a strategic marketing guy, which is part of the product definition phase, what, in their opinion, is the level of concurrency between product definition and design. So they ask, for instance, the marketing guys, which are responsible for product definition, what do you think the concurrency between your phase and the design phase is? In other words, how much work do you think you need to complete before the design guys can start working? What this means is that the marketing guy really thought that he or she needed to do only a little bit of work, let's say only 1%, or let's say this is 10%. If they only do 10% of their work, then the design guys should be able to do 40% of their available work. So they thought that they only need to do a little for the design people to start working a lot. This is what basically they thought. And you see actually, and the same with the product architect, but you see the design people actually had a completely different opinion. They thought that the product definition guys should do a lot of work before the design people can start doing just a little bit, right? So this is a very nice conflict of interest, you may say, a conflict of perception, which was made known by this approach. Now, yeah, this is not so important, and the summary. So we didn't have so much time this time, this lecture. There were a lot of things to explain. I will come back to slides which are not clear. And I mean, even if you understand everything, I would still address some of the slides on Tuesday in the self-study. And basically, if you just look at the figures in the papers that are available, all these slides are there. But in principle, you shouldn't be able to do it. You shouldn't have to do it. Thank you. The online test, you will have, let's say, 4 to 6 hours after you start it, but the whole online test would be available for maybe a week. So you will have 1 week to start it. But then once you start it, you have, 4 to 6 hours. If you don't think, if you try to find everything on the slides, it would take you maybe about 30 minutes, I think. About 30 minutes, 20, 30 minutes. But, the point of these online tests is not to make it possible to fail them, unless, of course, you don't want to do them, which is, there is nothing we can do about it. The point of the online test is to simply make you go through the slides. And just by going through the slides and find information, you automatically remember something. All right. Are there any questions regarding the previous lectures or self-studies? Because today we kind of start a new topic. You can ask questions later, and also you can ask any questions during the self-studies regarding the lectures. So let me start. Today I'm going to be using a fancy presenter, because those of you who have seen the slides, you saw that there are diagrams and kind of drawings that I simply need to navigate through. And if I use this laser pointer, you can see, but the people watching the recording cannot see. So this kind of makes it very difficult for people to follow these lectures only with the podcasts. So with this thing, I can do a lot of fancy things. For example, I can do like a spotlight thing, right? So for example, this is lecture 4. I can, what was it? I can zoom in. This is the professor. Yeah. And this is the email that you should send all your questions to. So yeah, lots of cool things. It kind of makes it difficult to navigate because when I move it, the cursor moves. But anyway, these are petty concerns. All right, let's start. Again, as I will do in every lecture until the end, and as you should expect from me in every lecture until the end, a summary of what we've done so far. We've looked at mostly finding solutions to problems that we already discussed, their nature. These are complex problems, non-trivial problems, multiple criteria problems, and we looked at ways to analyze the situation, to analyze the problem and find solutions for it, and then select what we hope to be the better solution, finally implement it. We looked at the problem-solving cycle as a framework for coming up with solution approaches and selecting solution approaches. We started with project management last lecture. Today we're going to finish project management. It's mostly about implementing solutions. We looked at how projects can be scheduled from time perspective, so the critical path method. Today we're going to be talking about some deficiencies of the critical path method and how we can address them. Hopefully you know the critical path method is the thing which determines your project duration, and we can also deal artificially, of course, with uncertainty in the critical path method by using this kind of buffers and floats, or buffers or floats. So if you have uncertainty, you can just allocate more buffers, which is kind of artificial because the nature of uncertainty is something that you cannot really predict. So the question is kind of paradoxical. How can you allocate buffer for something that you can't really predict? But this is one deficiency of the critical path method. What buffers are good for, however, is to shuffle resources around. So if you have a critical activity with no buffers, or with zero buffers, then you can shift some of the resources from tasks with a lot of float to it, and then hopefully speed up the whole process. We saw an example in the last lecture, and probably there would be a similar task required in the exam. All right. And the rest of the course is basically going to be about studying our solution. This should be just one question mark. This is not like a super existential question, but this is what the rest of the course is going to be about. Does the solution work? And if not, who is to blame? And I particularly like this lecture, today's lecture, because there's going to be an example precisely of this situation. The solution doesn't work, and two parties argue whom to blame. And they actually argue and settle this in court. And they use systems dynamics to do this, which is pretty amazing. They use modeling and stuff like this, which reminds me that today we're also going to be introduced to modeling. This system dynamics model that I talked about. You will not have to do any models for the self-study, not yet. But this is just a flavor of the models we're talking about, the so-called system-level models. We model the whole system, not the individual elements within it. All right. As I promised you last week, we're going to focus a little bit more on quality management. So quality. Last week we saw how time constraints can influence our project. Today we're going to see how quality constraints are going to influence our projects. And the quality, what is quality control in simple terms? In a kind of intuitive notion. What do you understand when somebody tells you, yeah, our project needs quality control? Yeah.
Measuring the outcome of the project against the objectives and goals that were set prior to the project's commencement.
Yes, that's true. And then what do you do after you measure the outcome?
After you terms of your quality control, you do the unit testing of what you have expected as a result.
And if expectations don't match reality?
Then you have two options. You generally define the problem into one or two categories, one of which is it actually something that is required for your delivery as a solution, or is it something that is there as an issue and you can live with it, and or it's something like it is something that is like a critical part of the project, so you cannot really deliver it.
What if it's something that is needed, you need to deliver it, but it doesn't work as you expected?
Then you have to stop the delivery and you have to fix it.
Fix it is good enough. I was looking for the term go back and fix it. Because quality control is nothing more than a feedback loop. And today we're also going to be introduced to feedback loops, which is going to be expanded in next lectures, but quality control is simply a feedback loop. So at some point in your project, and what these points are is also going to be introduced, you check your expectations in terms of quality. If something doesn't work, you just go back and fix it. It's not as simple as that, of course. Sometimes you can't fix it. Sometimes you need to account for propagating changes along your project. But this is what quality control represents, a feedback loop, nothing more. So today, what we saw already is kind of a sequential approach to project scheduling, right? We saw the critical path method. We saw the how you can break a project into subtasks. And these subtasks were either sequential completely or fully concurrent, fully parallel, right? If you remember the critical path, you can have a whole chain of tasks which are fully sequential, or you can have two tasks which are completely concurrent, completely parallel, but nowhere in between. What this lecture is going to be about is the so-called multi-phase projects. Because you see, in every big project, you can't just split things into subtasks and blindly going through all the subtasks. If you build a garage, like we saw the example in last lecture, maybe you can do this. But if you have to build a tunnel which spans 15, 20 years, or if you have to produce some software product or a microchip, you need to do more than just splitting into activities and tasks, and you need to do these kind of phases. And here we're going to be talking about the project life cycle, which is nothing more than the human life cycle, right? As humans, you're born, you grow up, you're mature, eventually you decline. Well, you decline and eventually you die. And it's the same with the project. It's conceptualized, this is one phase, then it's designed, another phase, it's implemented, and then finally it's decommissioned. So these are the multi-phase projects, and we're going to see that things get complicated when you have multiple phases, each with a different task. And this picture hopefully illustrates the idea. So here we have a project which starts from, let's try to do that now, which starts from here and then finishes here. And we have multiple phases within this project. It's up to you to define the phases. Different industries have different standards for defining project phases. And within each phase, okay, I shouldn't use. Good morning, everyone. Welcome to the fourth lecture in the Systems Dynamics course. Before we start, as usual, a few announcements. Now, on Monday, I went to the dentist, and no, I mean, I still suffer. So, actually, I cannot open my mouth so much. That's as much as I can open it. So, if at some point you don't understand what I'm talking about, just stop me and say something. That's one thing. Second thing, I would like to remind the presenting groups from last week to upload their student solutions. At least I didn't see them yesterday, I think in the evening. Is there anybody from these groups who presented last Tuesday? Have you uploaded your solutions? because I mean there may also be a problem with the Moodle system, because I may have set up the wrong things. So I want to know if you have problems uploading it or you just didn't bother. But I hope you will upload it by the end of this week. Another administrative thing, this is the 4th lecture. So after the 4th lecture, we'll have an online test. I already talked about these online tests. The online test will probably be prepared tomorrow, and you will have maybe from 4 to 6 hours to complete it, which is plenty of time anyway. In addition to that, there will be more about the online test. I will send an email around. In addition to that, there would be an online survey, which is the other quality control that we do in this course, where you kind of evaluate me. And it will also probably become available tomorrow or maybe on Saturday, I don't know. And then you'll have 1 week to complete this online survey. It's going to be a mixture of multiple choice questions and kind of a manual text input where you can write comments and stuff like that. And then we all discuss, so of course it's anonymous. Even to me, it will be anonymous. This is the point. But then we'll all discuss the aggregate results. And I'll show you what the majority thinks. All right. Are there any questions? Yeah.